All right, a little late start here. So we want to try to do a distortion energy theory problem, maximum shear stress theory problem. Do you want to do a basic one, or do you want to do something that's specific to a contextual problem here?
I think a contextual would be good.
Yeah. So we're in chapter 5. Let's just pick a problem out. They have a lot of ones. Well, here you go. Let's just do this one. There you go, 536. So we'll draw this thing out. We can make fun of the tablecloth. Get my real calculator instead of the stupid phone. All right, so maybe I'm gonna get some geometry out of the way. And so the area here is pi over 4.015 squared, 0.015 squared pi times 4 divided 1.767 e minus 4. And get the I, pi over 64, 0.015 fourth, and 0.015, raise it to the 4, times pi, divided by 64, boom. 2.485 e minus 9 m fourth, and j is just going to be 2 times I. So 2 times that, we get 4.970 minus 9 meters fourth. To get on the load side of things, it's almost a little ridiculous to do this, but hell, we should always do the right thing, right? And that's the z-axis, and that's the y-axis, and this is the x-axis going that way. So we will make an itty-bitty FBD, even though that's completely unnecessary. The only one we really need to do is in the xz axis, because looking at this thing, so simply, there you go. The torque doesn't show up, obviously. Here's reactions right there, RZ, RX, and we have a moment reaction. This is, what is this? This is the F of a 0.55 kilonewtons right there. And here's our 4 kilonewtons right there. And this thing's 100 millimeters. So that's going counterclockwise. So this reaction moment, M, call it Y. Or maybe I should keep using my R's, RY. MRY is reaction moment. So as dumb as it is, just go through the motions. It's a good idea. It's a good idea to go through the motions. So M here is about the y-axis. And we have MRY, negative MRY, plus 0.55 times 100, because it's kilonewtons and millimeters, so they will cancel each other out. So we get the MRY equal to, I think I could do this in my head, right? 55 Newton meters. Woohoo! And that's all we really need for the loads. So we go for the stresses. And it said in the instructions on this to do it at both A and B. So let's follow the instructions here and let's see what happens. For axial, we can see that it's just going to be that P divided by A, right? So P divided by A in this case, and it's going to be tension. So we get 4, I'll go 4,000 because it's 4 kilonewtons, so 4,000 divided by my area 1.767 E minus 4. Of going for speed now. Going for speed. That's not a good idea. That's not good learning. Learning doesn't take place just because you go fast, right? I get 22.64 megapascals in tension. We take a look at our situation up here, and I asked the question, do you think we had bending at A? Is there any bending at A?
No.
No moments, right?
Right.
You need a moment about Z to get any bending at A. So all the bending is going to be from B, and it's all going to be from this moment right here, this guy. And is that tension or compression?
Tension.
Yeah, you can even just, you can just see the things pulling apart because of that force right there. Or the same thing from this moment right here, right? From this reaction moment, that reaction moment's pulling at that point right there. So that comes tension, sure. So I don't know why I wrote axial like that. I meant to go axial like this. I meant to go, I guess, to write it over to the side and then to go bend. MC over I. So we're going to get our 55 Newton meters times our 1/2 of our diameter, 0.015 divided by 2, divide by our I of 2.485 E minus 9. And what are we going to get? 55.015. I think I got this right. It looks like 166 megapascals. And we said that was going to be tension. And that was going to be at B. Nothing at A. And then torsion. And so we're going to get torque, TR over J. And they told us it was 25,000. No, it's 25, right? Think the problem. I got to read the problem again. No, we're not on the problem. We got to go back over here. Boom. Yeah, just Newton meters. Okay, cool. When in doubt, look it up again. And we have the J of our 4.970 E minus 9. So 0.0152 divided and over 25 times, and then 4.97 E. Nice. Do that right? I think maybe I did. And I get 37.73 megapascals. Now, they did not say to ignore transverse shear, and we're also looking at specific stress elements. So let's actually look, let's check that out. Let's see how much it is. Transverse right here. And it's a circle, so it's still going to be 4/3 V over A. But now it depends on which point that we're looking at. So let's go back up here and say, which one of these is going to have transverse shear to it? A or B?
A.
I agree, A, right? And it's going to have our 0.55 kilonewtons. It's going to have that, right? So maybe we'll just say at A to help to remind ourselves. So we go 550. Well, I need that 4/3 in there too. I forgot. It's not going to be a lot, is it? 1.767 E minus 4. And so 550, right? 0.55. Yeah. Okay. I think I got it right. Okay. 1.767 E4 minus divided 4 times 3 divided. Okay. I get 4.150 megapascals. And looking at it, it looks to me as if the transverse is going that way, but the torque is coming this way. So they're actually going to, this torque is, it's going to, this transverse is actually going to reduce this.
Wait, so wouldn't the bending be 550 instead of 55 if you're going from kilonewtons to newtons?
I think it was because of 0.55 kilonewtons times
all right, yeah.
are 100 millimeters. Yeah, it's good. It's a good question because that's a really easy one to mess up on. Right. So it's good catch. A good look to catch, right? So if we're looking at element B, and here's element A. Element A, I didn't get it. I guess I could fit him on there, right? He would be like X, Z. And element B looks like he's going to be X, Y. All right, so this is going to be tension B. Tension of B is going to be due to both the axial and the bending. So the sigma X, or I might even go like sigma BX, is going to be the 22.64 plus my 166, if I got that right. So we get 188.6. And at B, we established that's only going to be the torque, right? Nothing, no, the shear at B it isn't affected by any of these other things. Right? So, whoops, I'm going to go back over here. Just double checking I'm still recording, right? Yeah, you're recording, okay. And so the torque is coming down the face like that. So that's 37.73 megapascals. Over here, it's only going to be the axial. So we get 22.64. And then, but now the tau, and we would call that maybe XZ right there because it's in the XZ plane, is going to be our 37.73 minus our 4.150. 37.73, 4.15 minus, we get 33.58. And it too is going to be in that direction, albeit, of course, it's not as much as the other one. So here's your 33.58. In this situation right here, if we're going to, this problem was only asking for distortion energy theory, if I read it correctly. I think I did. But might as well go for both of them. Let's see. You can't read it. It's too small for you. I'm probably. It says based on the distortion energy theory. Yeah. But we could do it for both. We could do it for both things. Might as well start some. I could do the von Mises stress right here. I got enough room. So for B, all I would do is be sigma x squared plus 3 tau xy squared 1/2. I almost screwed that up. And so that's 188.6 squared plus 3 times 37.73 squared 1/2. And 37.73 squared 3 times plus square root. I tell you, the Hewlett-Packard verse Polish notation calculators are so much faster. Become lightning quick. Sigma A, von Mises, I guess I'll write it out. This is going to be also x squared, but now it's going to be 3 tau xz squared 1/2. And now we get 22.64 squared plus 3 times r 33.58 squared 1/2. And now we're going to get, see, 22.64 squared, 33.58 squared, 3 times plus square root. And now I'm starting to think that maybe I forgot to do the 3 up here. I was moving too fast. So let me double check this one. 188.6 squared, 37.73 squared, 3 times plus square root. No, I got it right. Okay, I remember. So, and you don't need to say tension or compression when it comes to this because it's always just a value, right? You do a quick Moore's circle for these stress elements right here. By the way, I always think these battery little labels of the batteries are funny. It says keep away from babies, but it's like it says no babies, right? I just think that just makes me laugh every time I see it. So every time I replace a battery, I put that sticker somewhere. Little calculator battery warning. It's hilarious. Trust me. All right. So we'll do them in parallel here. Here's for B over here. We say that we have 188 and 37. Oh, that's a terrible. 188 and 37. This one, well, we actually get a little bit closer, right? So they almost like very close, similar to each other. Not that it matters. Here's your C and there's C. But there you go. And this point is going to be the 188.6 and 37.73. Oh, and actually, you know, I got it. I actually plotted it right on accident. I didn't actually meant to do that, or I didn't actually think about it. Just put it in there. But let me see if I can do this one correctly. Yeah, that's actually correct too. This is the 22.64 and a 33.58. You know, you guys know how to do all these right already, so I don't necessarily need to do all the things each time, but it's definitely good to like just double check on yourself. But you can, you know, looking at these things, I think it helps to like think your way through the problems here. So C is going to be 188.6 divided by 2. 94.3, and R is going to be, in this case, it is C, and 37.73 squared. So I need that squared, 37.73 squared plus squared, and I get 101.57, which is actually going to be the, in this case, because of uniaxial stress, that will be the abs max. But if we want to do that plotting thing, we need the sigma A is going to be C plus R, or 94.30 plus 101.57, and sigma B, C minus R, 94.30 minus 101.57. 195.9 and 94.3 and 101.57 minus, and we get negative 72.7 megapascals. I know I'll probably be boring you by doing this other one right here. I mean, I don't know, it's sort of redundant at this point, right? But what the hell? 22.64 divided by 2. Like I would say that one of my life skills I had to develop over time was being able to put up with stupid repetitive tasks without getting like overly bored, and just slogging through even though it was like repetitive, and just do it, you know. But as a younger man, I would complain about it a lot more. What did I just do? I was just about to do. All right, my mind's getting distracted. Let's see. I get back on track. 35.44. I think I might have. And that's the tau abs max. I think I might have made a mistake on that one. 33.58 squared plus squared. I got it right. Okay. So my sigma A C plus R, I don't need to write them out. It's 11.32 plus that goes 46.76. Sigma B C minus R, so go 11.32 and minus 35.44, and we get a negative 24.12 MPa. Okay, so now we want to get our safety factors. So DET right here. Let me go B DET. Going to be my yield strength divided by my von Mises here. So what I said, 280 divided by my 199.6. So 280, 199.6 divided, I get 1.40 for my A, DET, get yield strength, and here we go, 280, and we'll go for 62.41. And I get 4.49, call it. For maximum shear stress theory, we know that's the yield strength divided by 2, and that turns that into shear yield strength for us. And then we go abs max. And this is, of course, this for B. So we have 280 divided by 2 divided by 101.57. And we get 1.38. So you can kind of see, make a comparison. And then for A, I don't need to write that out. You get the idea. 280 divided by 2 divided by our 35.44. Is that right? Yeah. 280 divided by 2 and 35.44 divided. All right, so we get 3.95. And we can compare those guys together. We can see, yeah, okay, this is more conservative. But let's take a look at plotting. Well, first off, we might have the answer, right? So the answer might be in the back of the book, and that's always a fun thing, right? To try to, I don't know, fun. I don't know if that's the right word to use for it. It's probably like right there, right above it, right? And this is chapter 5, and it's problem 536. Oh, I didn't do it. How dare you? So let's go to solution manual. All right. This is the 10th edition, I think. And machine design, Shigley, 10th edition. I think it's very weird to have the solution manual in the 10th edition as Word documents. I don't know why. I don't know why they do that. I don't know. It's gonna wake up. And this is problem 536. Come on, just load. There you go. And they're even in like in a weird format too. You can't even edit these equations. So you would think that would be the reason why they would do it, right? At least that's what I would think. Oh, look, 1.4. That's what we got. And 3.68. Ooh, that's not what we got. Oh no, what are we gonna do? Oh no, no, it's not what we got. At A, why not? You can see what they did here. Okay, we got 2.6. Did we get 22.6? We sure did. And ooh, they added them together. I think they're wrong. Unless I drew the problem wrong. You know, there is a certain amount of thrill to finding somebody else's mistake, by the way. Yeah, I think they're wrong. Welcome to Wrongsville, population U, because that transverse should be going that way, and this shear should be going that way due to this. But not wrong by a lot, I guess, but it's wrong enough. But they get a 76 as opposed to our 62, but that's why. But we did get the right one. We do match right here, so that's exciting. But now let's go to assignments here and go to our failure loci. There's a dynamic solution. The dynamic solution exam. Okay. Because my computer is on auto save here, I'm gonna create this. I'll save this to a new thing here. So we will stick in here. Stick this in as what? 280. Boom. And we could be a little clever. I'm not directing you to do this, but you could if you wanted to, right? So I'm gonna go. Let's see. I'll go A and B. And no. I want to do this. What do I want to do? I'm trying to think on the fly here. I'll go sigma A and sigma. Oh. I'm sorry. My bad. I'm not a smart man today. Or most other days. Sigma A, sigma B. And I'll just plug in the numbers for this. All right, so the principal stresses were 195.9 for A and negative 72 point, where'd you go? 72.7. I'll put these in here as well. We found this was 46.76, and we had negative 24.12. And how do I want to do that? I'm going to go 0 and 0 here, and 0 and 0 there. Okay, so I'm going to plot this. No, here I got to do this. I got to add this in here, and in select data, add my x values right there, and my y values right here. Boom. There you go. I could also do this one too. Let's see, I'll do this one. Let's see what it looks like. X values there, Y values here. Yeah, that's not an exciting one, is it? But you can see what I'm doing here, right? You understand what I'm because I don't have this thing printed out, so doing it graphically doesn't really do much for me. But wait a minute. I'm a little concerned here. Wait, that doesn't seem right. I got 1.4 and I got 1.38. That doesn't look right to me. 195.9. Okay, that looks right. And then 72, that looks right. But this 280, the 280 up there. This thing is way too close to that maximum shear stress theory line. Huh. What's going on here? Why would that be like that? Did I do something wrong? Oh, wait. No. See that line right there, it's just way too close to this thing. It would get a safety factor that was really approaching 1 right here. And I don't know why. Did I do something wrong? I don't think so. 199.6 and 280 is 280. Huh. Everything looks correct, but this is just I'm just a little flummoxed by that. I wonder if no. You guys are still there, right?
Yeah.
Trying to think my way through why these are. Well, this one makes sense to me. That looks like really far away. But this one, I got it's plotted at the right point right here. My dog's excited about the mailman, some mailman or something.
Why is it a problem if it's that close?
Well, because my answers are 1.4 and 1.38, right? So
right.
The proportions should be pretty far away from this thing. But look how close that is right there.
Is that too? So you're graphing for that line. What numbers you're graphing? The orange line, the 190.
The orange line is the 0 to 195.9 is the x direction, right? And the y direction is to negative 7.2. So it looks like it's kind of plotted out to the right spot right there, right? Yeah. 195.9 and negative 72.7. And the maximum shear stress theory looks like it's correct. It's going from 280 to 280 right there. So I'm just curious why it isn't doing the thing it should be doing. I mean, for the maximum shear stress theory, I get a safety factor of 1.38. This looks like it might have been a safety factor of like 1.05.
Yeah, it's pretty close to 1.
Right? Yeah, it's going to be like really, really close to being on the line. And I can't figure out why. It doesn't make sense to me. If I could have done something wrong. I mean, this never works. This always seems to. I've never had this problem before on this. I don't know. I'll have to think about it some more and get back to you.
All right.
Yeah. But anyway, that's the technique. Even though this right here is making me curious as to what the results are. Because graphically, right here, that doesn't feel right. And as I've mentioned before, this usually works out pretty well. Huh. I'm flummoxed. But I got the right DET, right? I got that one at 1.4. It's just my maximum shear stress theory is actually, I mean, this could possibly be 1.4 for the DET, but I seriously doubt the 1.38 for the maximum shear stress theory for how close that is. So I must have done something wrong in this calculation. So let me double check this guy right here. Strongly suspect an error. 280 divided by 2 divided by 101.57. Yep, I get the same thing. And that was my let me check these guys in here. 94.3 squared and 37.37 squared. Add them together, take the square root, and we get 101. Now I get 101.4, but that's just a little bit different. I don't know. Anyway, we're probably time's up. Well, the calculus people aren't bothering us today, at least. Just so you know, next week I'm going to cancel because I'm traveling.
All right, sounds good.
Okay, if you can help me remember to make the announcement in class, I'd appreciate it. Just to anybody else might want to come around. All right, I appreciate that. Thank you. All right, guys, have a great weekend.
Thank you. You too.
And I will sit here and ponder this, and I'll get back to you maybe.
All
hopefully,
right.
if I
don't ponder too long.
I won't. No.
Just
long enough.
Have a great weekend.
You too.
Bye.
Bye.